Next, we go to our topic, which is the first law of thermodynamics. Since we are through with our review of our basic definitions and concepts regarding the first law of thermodynamics, this law is often called the conservation of energy law, and this is essentially true as we discuss further. Our procedure will be to state this law for a system or given a control mass undergoing a cycle, and then for a change of state of a system. After the energy equation is formulated, we will use it to relate the change of state inside a control volume to the amount of energy that is transferred in the process as work or heat transfer. When a car engine has transferred some work to the car's speed is increased, so we can relate the kinetic energy increase to the work. Or, if a stove provides a certain amount of heat to a pot with water, we can relate the water temperature increase to the heat transfer. More complicated processes can also occur, such as the expansion of very hot gases in a piston cylinder, as in a car engine, in which work is given out and at the same time heat is transferred to the colder walls. In other applications, we can also see a change in state without any work or heat transfer, such as a falling object that changes kinetic energy at the same time it is changing its elevation. The energy equation then relates the two forms of energy of the object. So, the first law of thermodynamics, when we consider a cycle or during a cycle or any cycle a system undergoes, the cyclic integral of the heat is proportional to the cyclic integral of the work. So, this one, you have the cyclic integral of heat is this is proportional to the cyclic integral of work. In this case, we will use the inexact differential of Q and the inexact differential of W. So you can also write this one as Q. This is equivalent to that one. Or So where J is the proportionality constant. So in a system undergoing a process, there is or undergoing a cycle, meaning you have our PV diagram. So this is 1, 2, 3, and 4. So this is an example of a cycle. Okay. So the first law of thermodynamics for a control mass undergoing a cycle. So let's illustrate this law. So considering here we have this figure. This is a paddle wheel and it will rotate. Then we have a weight. So as there is lowering of weight here, the paddle will rotate. Okay. So as it rotates, so there is heat. Example, we have a gas here. As the paddle rotates, and there is heat. Okay. So the symbol cyclic integral in the exact differential of Q, which is called the cyclic integral of the heat transfer, represents the net heat transfer during the cycle, and this is the net this is the net heat transfer during the cycle. And the cyclic integral of work this is the net work during the cycle. So cyclic integral means the system undergoes a process, and that process is called a cyclic process. Okay, in our previous discussion we define a cycle wherein its initial state or the initial and final state are equal. Okay, so the basis of every law of nature is experimental evidence, and this is true also of the first law of thermodynamics. Many experiments have been conducted on the first law, and everyone thus far has verified it either directly or indirectly. So for those experiments, the first law has never been disproved. Okay. So we know that the units of work and heat for any other form of energy either are the same or are directly proportional. In SI units, the joule is used as the unit for both work and heat, and for any other energy unit. So it is the joule. It is the unit in SI measurements. And for English units, we have that BTU. British Thermal Unit. This is BTU. Okay. We're in 1 BTU is equivalent to 778.17 foot pound force. This unit is termed as the International British Thermal Unit. For much engineering work, the accuracy of other data does not warrant more accuracy than the relation 1 BTU is equals 778 foot-pound force, which is the value used with English units in the problems in this for some problems. Because these units are equivalent, it is necessary to include the J, or the proportionality constant, but simply to recognize that for any system of units, the equations must have consistent units throughout. So therefore we can write the cyclic integral for the basis of consistency of units. So we have here the cyclic integral of the inexact differential of Q is equivalent to the cyclic integral inexact differential of W. So this can be considered as the basic statement of the first law of thermodynamics.